this is a set of tutorials that, so this Hello Qiskit game is a set of tutorials that is provided as part of the Qiskit textbook. So actually we're here at the Qiskit textbook now. It's called Learn Quantum Computation Using Qiskit, and it has various chapters taking you through the basics of qubits, as well as algorithms and algorithms for nearer term applications, things related to the hardware, things related to pulse level control, and of course exercises, games, and demos. So I would encourage you to visit this textbook and read some of these chapters. However, in this session, we'll be just going through some of the same sort of content as the first few sections, but in the form of this game, which you can find here. So the way you play it, it's interactive. It works in the browser. So you have to click try, and then it will go into the mode where it actually tries to do things. And then you can say run, and it'll have to set up a kernel, which admittedly takes a while. So after that has happened, you'll know it's happened because all this particular cell has to do is print hello, I'm a code cell. Once you see that, you'll know that it's set up, and you can continue by, so there we go, we've done it already. Then we can do the second one, which imports the tool that we need here. And then we can move on to the actual puzzles once this is imported. So hopefully this is working for all of you out there as well. If it isn't, then probably the best thing is just to keep on listening to me and try again later. I don't think we should focus too much on trying to fix any technical issues at the moment.
James, sorry for interrupting you. I just want to encourage people to use the Q&A section and the chat button for asking questions. We are working in the background for helping them. Sorry.
Yeah. So if you do have technical issues and you want them solved now, then the rest of the team will try and do that. But I will just carry on because we do have 2 hours, but 2 hours disappears very quickly. So yeah, get help from the other people, and I'll carry on by going through these exercises and explain what's going on in them, because the whole point of them is to try and teach people about single and 2 qubit gates and single and 2 qubit states. So what we have is a visualization of the states and also a visualization of how to manipulate them. And this first section is this first section of puzzles is actually about bits. So we don't even get onto the quantum element yet. We're mostly just introducing how we are going to represent bits and gates in this sense. So here we have a black circle, and this black circle represents one single bit. If it is black, it is in the state 0. If it is white, that it is in the state 1. And we have initialized this bit in the state 0. So there it is, it sits there. Let's do something to it. Basically, the only thing you can do to a single bit that is in any way useful is change its value. So we do that by something called the NOT gate in classical computing. So let's apply that to the only bit, and we find that it becomes white. And this is a very simple puzzle. All you have to do is apply the NOT gate 3 times and see it turn that bit on and off, and then you have completed. Now that is not very exciting. So let's take 2 bits, and now we can do something like, well, here we have an exercise which is to turn the other bit on. So let's do a NOT on the other bit, and it turns it on. So now we have mastered a NOT gate. Right. Now we have to do something a bit more interesting, which is called a controlled NOT. So what a controlled NOT does is it is a 2-bit operation. So we use it in quantum computing, but you can also think of it as something in classical computing as well. It's a reversible form of the so-called XOR gate. So it is a 2-bit operation. It looks at 2 bits, and what it will do is apply a NOT to one of those bits, controlled on whether or not the other is turned on. So if you have one of your bits is the control, it determines whether basically whether the NOT gate actually happens, and the other is the target, which is where the NOT gate would be applied. So when we apply controlled knots in this case, we choose, it's going to involve both of the bits, so we choose the one on which the knot would be applied if it actually happens. So if we, for example, choose the bit on the left, that would mean if the knot does happen, it would flip this from being on to being off. And let's apply it. Nothing happened. And that's because this one, which is acting as the control, is off. And when that is off, nothing happens. But if we did it the other way around, with this as the control and this as the target, then this is on. So when we do the controlled knot, something will happen. What will happen is that there will be a knot which flips this from on to off. Oh, sorry, from off to on. So we do that, and exactly as I described. So the puzzle here was asking us to use a controlled knot to turn on the bit on the right, and that is exactly what we did. Okay, so let's do the next one. Now we can just, we have no more additional operations anymore, so it's just becoming comfortable with what we have already. Use some controlled knots to turn the left bit off and the right bit on. So currently the left bit is on, the right bit is off. We want the opposite to happen, so we can use the controlled knot to turn the right bit on. We're halfway there. And then given that this is on, now we can use a controlled knot, controlled on that to do a knot over here and turn that one off. So these first few exercises are just getting you familiar with the notion of controlled knots, not with the complexity of quantum gates, but just in familiar bits, just using our visualization. Okay, now we are going to start exploring why there is a big grid here that is empty and what information might be encoded there. Here we have a circle which is neither on nor off. It is not 0 or 1, it is gray. And what we're using that to depict in this visualization is a bit which has a random value. So it is 0 or 1, we just don't know which. It will, when we look at it, it will give us a random value. So we can still think, well, before we look at it, before we learn what its value is and update our information, what would be the effect of performing a controlled knot? So here we can, the point of the exercise is to make the bit on the right random using this controlled knot. And what we could do is simply do a controlled knot controlled on this random bit, targeted on the other bit. And if this one is randomly off, then nothing will happen over here. It will remain off. If this one is randomly on, then this one will be flipped and become also random. So let's do a controlled knot targeted on the bit on the right, and we have them both random. However, if we think about what happens here, we can realize something. There is a deficiency in our visualization. This is telling us these are both random, but this could mean that they are both independently random. That the value you get from one doesn't tell you anything about the value you would get from the other. Or it could mean that they are random and anti-correlated. So maybe when this one gives a 0, you know that this one is going to give a 1. But neither of those two cases are true in this instance. The way we have constructed it, we know that whenever this one is a 0, this one is also a 0. Whenever this one is a 1, this one is also a 1. So they are correlated. So there's these different cases that could occur. They could be random, independently random. They could be random but correlated. They could be random but anti-correlated. And we need some way to keep track of that information if we are to use this as a good way of keeping track of the states of bits. And so for that reason, we are going to introduce a new element to our visualization. And I should just say that this visualization is one way of visualizing quantum states. Well, at the moment, they're classical, but we'll move on to quantum. There are many ways to try and take the linear algebra that represents quantum states and present them in a more visual form. For single qubits, we have what's called the Bloch sphere. For 2 qubits, we can use all kinds of methods. There's the Q sphere that you might see in the IBM quantum experience. But every visualization has its pros and cons. Everyone is useful for different purposes. So what we're exploring here is one that is particularly useful for the purposes that we are, for the things that we are learning in this tutorial. So yeah, let's get back to what we're doing here, we have this additional circle. This is going to give us information about correlations. If it is gray, that means that there is, well, let's say if it is black, that means, well, let's make sure I get this right. If they are certain to agree, it is 0. It is black. If they are certain to disagree, it is white. So whether it's black or white tells us whether they're correlated or anti-correlated. And if it's random whether they agree or disagree, then it is gray. So in this case, this one is random and this one is always off. So it is random whether they agree or disagree. So this one is indeed gray. However, if we apply the same C0 we did last time, we have 2 random but correlated bits. The fact that they are correlated is now encoded in this piece of information. And if we flipped one of the bits, they would become anti-correlated, and that is encoded in this being white. So now we have pretty much everything we need to know about bits, and there's finally one example where we have to turn on this bit, fully on, not random. So we can do that by correlating these. Hang on, we'd have to do a not first, so that actually does something. Actually, what am I doing? So just because I created these puzzles doesn't always mean I know what I'm doing. Yeah, so we can find a sequence of operations which does indeed lead to what we want, which is the one on the left being, the one on the right being definitely 1. Now we can get on to what we actually are here to learn about, which is qubits. So qubits are basically bits in that they are objects, and if you ask them for an output, the only possible answers they can give you are 0 and 1. So there is no additional information that they can give you beyond that. But they differ from classical bits in that there are more ways to ask a qubit whether it's 0 or 1 than you would have on a normal classical bit. A classical bit is just 0 or 1. We don't even think of the concept of asking it what its value is typically, because that is not a significant event in the life of a bit. It is just 0 or 1, whether we're looking at it or not. Whereas a qubit, there are different ways that we can inquire whether it's 0 or 1, and so the one that we use determines the output, or has an effect on the output we're going to get. And when we do that event of asking it, that is something that has to be very much taken into account when we are thinking about the evolution of the state of the qubit. So it's a significant event in the life of a qubit when we ask it what its value is. We refer to this event as measurement, and the fact that we can do it in different ways are called different measurement bases. When you in Qiskit use the measure command, you're using a so-called Z measurement, but there are also things called X measurements and Y measurements, and actually an infinite array of different kinds of measurements that you can do. But we are not going to do an infinite array of different types of measurements at the moment. We are going to do, well, but mostly people who work in quantum computing will typically focus on the Z measurement. And for those who do need to take into account that there are other different types of measurement, we'll always additionally take into account the X measurement. And then, if they go one step further and acknowledge 3, then there's the so-called Y measurement. And once you've got those 3, you actually can write down a complete description of a quantum state. So you don't actually even need to go to the infinity most of the time anyway. So what we are seeing here is a representation of a qubit state. So just like the bit, we have a circle here, which is here on. But the difference is that we have another circle over here. Now this is not representing another bit. In fact, these two together are representing a single qubit, but they're representing different ways that we can ask its value. If we do a Z measurement, which is the standard measurement you apply to a qubit, then this one will tell us what the value will be. And if we do an X measurement, then this other one is telling us what the value will be. So here we see a representation of one single qubit. If we took that and did an X measurement, what we would find, if we did a Z measurement, we would find that it would definitely give us the output 1. But if we did an X measurement, it would give us a random result. So that is what this visualization is showing us here. Now the puzzle is again not much of a puzzle. It's basically a sequel to the first puzzle, where we had a NOT gate, and the NOT gate allowed us to flip the value of the bit, and we had to do it 3 times just to see it flashing on and off. So the X gate is basically the quantum version of the NOT, and let's apply it. We see that it flips the value of the output for the Z measurement. So that's what it does, and now we can move on. So now we have another puzzle, which is basically doing the same thing. We need to turn off what I'm calling the Z output. So this one here, the output that we would get for a Z measurement, let us turn it off, and we know that that is exactly what the X does. Now we are going to make things a little bit more interesting by having another qubit. So the second qubit is just like the second bit when we were looking at the early puzzles. It lives on the other side. It's again composed of 2 circles, 1 for the Z measurement and 1 for the X measurement. And if we do an X on this qubit, then it flips that value. Where the real interesting stuff comes in is when we start to combine 2 qubits. But first, let's look at doing some, as you've seen from the X doesn't actually change this value at all, the output for the X measurement. So here I should note that it's a little bit confusing, the fact that it's called there's something called an X gate, and there's something called an X measurement. There's also something called a Z measurement and something called a Z gate. And once you get into the linear algebra of quantum, then it is not confusing that these have the same name at all, because you see how they come from the same origin. However, in this case where we're not going to be looking at the linear algebra, it's a little bit annoying and not entirely obvious why they have the same name. So you're just going to have to bear with it, I'm afraid. But here we have another gate. It's called H. Let's see what it does. So this one was off and this one was random before. Now they're the other way around. That is basically what the H does. It just swaps the information between these 2 channels. Whatever was true of the Z measurement before you do an H is true of the X measurement after. Whatever is true of the X before is true of the Z after. Okay. Now what we've started to see below our puzzles is this. This is actually the quantum code, the quantum program that is behind what we're doing. So here we're saying that there is a quantum register, which is our 2 qubits. We are setting up Q, which is our collection of 2 qubits. And we also have a classical register, which is where we are writing the output at the end. And then we define the quantum circuit. And actually, when we did the Hadamards, we should have seen Hadamards being added to this circuit. And it's a little bit strange that they're not. Let's keep an eye on that. But in general, we should be seeing the circuit here. If we actually create the circuit, if we visualize the circuit using tools in Qiskit, we do see the 3 Hadamards, which is exactly what we were supposed to see. So we can now run this cell below the puzzles and see a visualization of the circuits that we're creating. So it gives you a connection between what we're doing in the puzzles and of course how you would actually create circuits in Qiskit, which is what you would ideally want to do after learning about single and 2 qubit gates here. Okay, so here our goal is to turn the Z output fully off. However, there's a little bit of a complicated aspect of this puzzle, because it also gives us restrictions on how many times we're allowed to use different gates. We can use the H gate as many times as we like, but we have to use X exactly 3 times. So to have this fully off would mean we could just do 1 H. It would then swap these values. And so this being fully off here would become fully off there. So we would go from a qubit, which is random for when we do a Z measurement, and definitely going to give us a 0 for an X measurement, to a qubit, which would definitely give us a 0 for a Z measurement and be random for the X, which is what we have to get to solve this puzzle. However, the puzzle arbitrarily tells us we can't just do one H, but we have to do H as many times as we like, but we need to use X exactly 3 times. So just using a simple H is not going to help because we haven't used the X 3 times. However, if we were to use the X 3 times, now it would turn it on and then off and then on again, which again is not what we want. So what we can do is move that back over there and do an X, because what we find is that the X does not affect the output of an X measurement. And if you do an X on a random value, then it's just still random afterwards. So we have created a state such that the X gate has no effect. We can burn our spare X gate by creating such a state. Then we can do our Hadamard. We can use the other 2 X's to turn it on and turn it off, and we're there. So this is just a way of showing how to combine different gates to get effects that we want. It's a bit of an arbitrary example, because why were we given this restriction that we had to do 3 X's? Well, just because that's what it said in the puzzle. But in general, you will find in quantum circuits, you have a certain amount of gates that you can do. You have an effect that you want, and you have to find creative ways to combine the gates to get the effects that you want. So here we can see our circuit that we performed. Okay, now we have been using the X gate, which flips the value of the Z measurement. Now let's look at a gate which flips the value of the outcome for an X measurement. And what does that? Well, it's called Z because of this annoying naming scheme. So if we apply this, then we find exactly it just turns this on and off. So we didn't have to do very much in that puzzle. So by combining gates, we can get new effects, and that's exactly what I said earlier. So as a simple example, by combining Z and H, we can do the job of an X. So here's an example where we have a puzzle where we need to turn this on. And so if we had an X, we know that X just turns this on and off. We could just apply that X, and then it would do it. But we don't have an X. So what do? Well, we have a Z. A Z turns this on and off, which is not going to do very much at the moment because it's just random over there. So Z does absolutely nothing. However, if we use an H, then we move that piece of information exactly into the place where we can manipulate it using the gate that we have. We can flip it, and we can move it back, and we have success. So let's run this again. So we need something that has the effect of an X gate, and we did that by doing an H, a Z, and then another X. So let's have a look at this circuit. So this is what we created. We have H, Z, H, and this is doing the effect of an X. And this is actually one very important relation in quantum mechanics, which is used quite often when you're transforming gates in formats that you want. It's something that is used indeed in the way that you do compilation before you run gates on real devices. If you wanted a controlled Z gate, then using the fact that our hardware only does controlled X gates, it will use a trick like this to do that. So this is not just an arbitrary little puzzle, but actually one of the important things to know when designing quantum compilation or designing quantum algorithms. Okay, so I lose track of all of these mini puzzles. So what is this one supposed to teach people again? Yeah, so one thing that you might notice is in any example we've seen so far, when one of these is certain, so when one of these circles is either on or off with certainty, and so will give a certain output to a measurement, the other one is always random. And this is an example of what's called the Heisenberg's uncertainty principle. These two different ways that we can ask a qubit whether it's 0 or 1 are complementary observables that are governed by Heisenberg's uncertainty principle. If one of them is certain, then the other one has to be random. And if that weren't true, then these wouldn't be qubits. They would just be two bits sitting next to each other. The fact that they have this relationship, which means that knowing one means that you inherently don't know the other, is what makes them what they are. Yeah, so in this example, we have to make the X output, so this one, be off, and the Z output be random, so we just need a Hadamard. So this is mostly here to allow me an opportunity to tell you about Heisenberg's uncertainty principle. However, we can have more interesting examples than just one being certain and the other being random. For example, here, I hope it's obvious, or at least you can believe me when I say it, but these two are not black, they are dark gray. So this is our way of representing in this visualization the fact that these, if you ask them what their value would be, they would be most likely to tell you 0. There would be a bias towards 0, but it would still be a little bit random. So here we have an example where it's not the case that one is certain and the other is completely random, but you can also share the certainty between them. So these two are now, the Heisenberg's uncertainty principle allows them both to be a bit certain. So we have an example where both of them are as certain as they can both be while still obeying Heisenberg's uncertainty principle. In this case, we need to make them both light gray, and so biased towards 0, biased towards 1 instead of biased towards 0. So we can use a Z to flip this one, and we can use an X to flip the other one, except, well, you know, I've got to make it hard for you, so there is no X. But we can swap that over there and use another Z. Okay. So now we have basic tools to manipulate single qubits. We have to get to the point of doing something more exciting, which is doing 2 qubits at once. So here we have our qubit that we've been looking at for a while now, the qubit that we were just manipulating here, whereas we also have the old qubit back, and we can do things that involve now 2 qubits. So let's just do some single qubit gates firstly, to see how they work when we have both qubits enabled. The point of this puzzle is to make both Z outputs random. So this should be gray and this should be gray. And we can, of course, do this with a couple of Hadamards. This Hadamard flips those 2 values. Hadamard on the other qubit flips those 2 values, and we have what we need. But again, now we have this case where this is random and this is random. But if we were to make a Z measurement of both of those, and we were to get those values, we know that each of them, if we look at it independently, would seem random. But what if we look at them together? Are they correlated? Are they anti-correlated? Are they completely independent? Are they something else? We need to represent that information. How do we do it? Well, we do it in exactly the same way as before. We reintroduce this circle here, which is going to tell us how correlated these 2 circles are. So that's the next puzzle. Actually, did I miss a puzzle? No, I do indeed go all the way to that point. Okay, so here we have this circle, which is telling us how correlated these 2 are, in exactly the way that we had when we were looking at bits before. So that is the job of this circle. It's not a new bit, it's not a new qubit. It's just telling us how correlated how correlated the results would be if we made Z measurements of both qubits. And this one is telling us how correlated the results would be if we made X measurements of both qubits. So it's telling us how correlated this circle is with this circle. But then what if we make a Z measurement of this qubit and an X measurement of this qubit? Well, that is the correlations there are being told by this circle. So we can think of, well, we take a line from here and a line from there. This is where they intersect. And similarly over here. So these are the 4 correlations which we now need because we have to take into account correlations depending on how we choose our measurements. So you don't usually have all of this information at your fingertips when you have a couple of qubits. But you do need to keep track of that information if you are writing down the state of 2 qubits, and so that is what we are doing in this visualization. So that's why we have it all here. The idea here is to make the Z outputs certain to disagree. So what is the state that we actually have? The X output is certain to be 0. The X output over here is also certain to be 0. So if we made X measurements of both, they would be certain to agree because they would both agree at being 0. But we need to make the outputs for the Z measurements disagree instead. So let's just stop them being random at first, make both of the Z outputs agree. So now we've done one Hadamard. This is certain to output a 0. This is certain to output a 0. If we do a Z measurement here and an X measurement here, so we see that those two are certain to agree in this case. We do another Hadamard. We now see the outcomes for Z measurements are certain to agree. We don't want them to agree, we want them to disagree. So let's just make one of these 1 instead of 0, and job done. Okay, yeah. So now we're going to make the X outputs certain to agree. So basically we just have to undo what we just did. Let's make the outcomes for X measurements certain to agree. Oh, sorry, disagree. And then let's flip one so that they agree. And, oh, sorry, I used an X, which flips this value. Well, actually it was going to flip this value, but that's not what I want to do. I need to do a Z, of course, to flip this one up here. And they both now agree on being 1, so we have success. So there's now still two new circles to explain. There are puzzles that you can do to explain those, but I'm not going to do that because I've already explained it. So now let's do something a little bit more exciting. I keep saying we're going to do something more exciting. I hope the excitement is ramping up for you at home. So now we have a case where things are not just black and white, but shades of gray. This one is most likely to output as a 0. This one is most likely to output a 1. This is most likely to output a 0. This is most likely to output a 1. So we have this one and this one, because they're both most likely to output 0s, are most likely to agree, but not quite as likely to agree as each one of them is to be 0 because there's the randomness of the other one. Anyway, let's not get too much into probabilities in grayscale form. The idea here is to turn on the 2 Z outputs as much as you can. So they're both off at the moment, and so we simply need to do an X to both this qubit and that qubit. But let's firstly think about what that's going to do. We know that the X flips this value, but what's it going to do to anything else? This value is telling us what the value of the Z, so it's telling us what's going to happen if we do a Z measurement, and it's telling us we're most likely to get a 0 for that Z measurement. This one is telling us if we do a Z measurement here and here, how likely are they to agree? And because they're both most likely to come out 0, they are most likely to agree. However, if we were to flip this and make it a 1, then that means that these now are most likely to disagree. So it will not just flip this value, it will also flip this value. And because this relates to a correlation with the Z outcome of here as well, it will also flip this value. So an X actually flips all along this row. And let's see that in action. That's exactly what it did. And now this X on the other qubit will flip all along this row, making this light and these two dark. And that's exactly what it is. And now they're mostly on, which is what this puzzle requires. Okay, similarly, we can think of an H as affecting rows. As I said before, the effect of the Hadamard gate, the H gate, is that whatever was previously true of Z whatever was previously true of the outcome of a Z measurement before we did the H is true of the outcome of the X measurement after, and vice versa. So that also means that if the Z measurement here is most likely to agree with the Z measurement over here before the H, then it means the X measurement here is most likely to agree with the Z here after the H. So actually the effect is that this whole row gets flipped with this whole row. And we can see that if we do the Hadamard. Now what we were supposed to do again, turn off the X outputs. Okay, let's now do this, a Hadamard over here, which is going to flip this row with this row. Let's see that in action. And now they are both on, but we want them to be both off. So let's do a couple of Zs to have that effect. And we are successful. So that whole level was teaching us single qubit gates on 2 qubits. And it was teaching us quite a basic set of single qubit gates, but these are fundamental ones in understanding how to move information around a couple of qubits. So let's now move on to 2 qubit gates, which is where we start to see the ability to create correlations or manipulate correlations, create effects like entanglement. So what we have here is the CX gate, also known as the controlled X or the controlled NOT. And this works exactly the same way as the controlled NOT that we introduced for bits. There are 2 qubits involved in a controlled NOT. One is the control, the other is the target, and it will do an X to the target if the control is, well, that's where it becomes complicated. If the control is in the state that it's certain to output a 0, the controlled NOT does nothing. If the control qubit is in the state where it's certain to output a 1, these are both, in both cases, for a Z measurement, then the controlled X simply does an X to the target qubit. So what we see here is that this qubit is certain to output a 0. So if we use it as the control and choose the other qubit, qubit 0, to be the target, nothing happens. Whereas if we do it the other way, we choose this one to be the control and this one to be the target. Because this is on, because it's certain to output a 0, sorry, a 1, if we do a Z measurement, then it flips the other one to on. It simply does an X. Now this is, you can think of this almost, well, this effect that we see in this specific puzzle, you could do in a non-quantum way. You could measure your control qubit, you could see whether it's 0 or 1. If it's 1, then you apply an X gate to the other qubit. And that would just be using measurements and single qubit gates. But that is not what a controlled NOT does. A controlled NOT is doing it in a truly quantum way, which actually allows it to have interesting other effects. So as well as the controlled NOT, there's also the controlled Z, and it's in looking at the relationship between the controlled NOT and the controlled Z that we start to see some interesting properties. So the controlled Z is exactly the same as the controlled X. So the controlled NOT is also known as the controlled X, and we call it CX in Qiskit code. And so the controlled Z simply, again, has a control qubit and a target qubit. It effectively, but not actually, looks at whether the control qubit is in the state which is certain to output a 0 or a 1 for a Z measurement. If it's in the state that is certain to output a 1 for a Z measurement, as this qubit over here is in this case, then it will do a Z to the target qubit. So in this case, let's choose qubit 1 to be our target qubit, and we see that the effect of the Z does indeed happen, flipping these values. Okay. So an interesting thing about quantum gates is there's often multiple ways to explain what they are doing, and these explanations can sometimes seem completely incompatible, but they are actually equally true. So in this puzzle, we explain the effect of this controlled Z as looking to see what this qubit was doing, and if it was in a state which is certain to output a 0 for a Z measurement, it does nothing over here. And if it's in the state that is certain to output a 1, as it is, then it does a Z. However, actually, what we were supposed to turn, well, okay, we didn't do what we were supposed to do in this puzzle, but this puzzle is supposed to teach you about stuff, and that's what we did do. So in this case, it's the same as the last exercise, but the qubits are reversed. So let's run it. So what we actually have to do in this puzzle is turn on the X output of Q0 and turn on the Z output, turn off the Z output of Q1. So in the end, we want this actually to be off. And this may be the puzzle which doesn't work. There is a bug in one of them. Yeah. So actually, let's move on to this one. Another completely different but equally true explanation of the controlled Z. We can think of it in terms of circle being swapped, like the H gate. In the H gate, when we apply an H gate, for example, to this qubit, we think of it as these two being swapped, and then these two being swapped, and then these two being swapped. We can also think of the CZ in terms of things being swapped. Now, also there is an app called Hello Quantum that you can visit, and we get especially nice visualizations, animations of this effect if you use the app. But let's proceed with not having animations. So now we're going to do the control Z twice with each qubit as control and see what happens. Now that's all we have to do in this puzzle. Just look at what happens when we do gates. So we'll do the controlled Z with qubit 1 as the target, and we'll see what it does to this specific state. What we found is that this one was black, and now that black circle has moved here. This one was white, and that white circle has moved here. This one was white, and that white circle has disappeared somehow in a mysterious way. Let's do it again. And we see that this set of swaps again occurs. This black now has moved back to where it was. This white has moved back where it was. This white has come back from whatever mysterious place it was located. We'll see where it goes later. If we do a controlled, so now we're going to do a completely different controlled knot, not targeted on qubit 1, but targeted on, on qubit 0, but instead we're going to do it targeted on qubit 1. What different effects does it have if we apply the controlled knot the other way around? Well, it does exactly the same as it did before. So actually, the effect of the controlled knot is, what's the word? Is symmetric. It doesn't matter which way round you apply it. It doesn't matter. You can tell yourself this story, as we told earlier, that there is a control and a target, and it looks to see whether the control is doing such and such, and if it is, it does something to the target. And that is a nice story that we can tell, and it's a nice way of motivating how we use it in algorithms. But we just have to remember that if we look at actually fully how it affects a quantum state, it's completely symmetric. It doesn't care what we think is the control and the target. It just acts in a completely symmetric way. And that means that there are two completely different interpretations of what a controlled Z is doing. We can interpret it either way. Both are completely valid ways of explaining the controlled Z, but they are also seemingly completely incompatible. Now, firstly, we should mention where that weird circle went, what mysterious realm it disappeared to, and this is the reason why it disappeared is because we're not actually fully representing the state of two qubits. There is not just the Z measurement and the X measurement. You may have noticed that if there's a Z measurement and an X measurement, where did the Y measurement go? Surely there should be a Y in between Z and X, since as we all know from primary school, that usually happens in an alphabet. So yeah, there is also the notion of a Y measurement, but I mostly kept it off this visualization to keep things simple. but here is a more full and complete representation of a qubit state, with this circle representing, as always, the outcome of the Z measurement, this circle, as always, representing the outcome of the X measurement, and this one representing the outcome of the Y. And then everything else is also correlations. So here is, for example, the correlation between an X measurement here and a Y measurement there. And we see that the controlled Z disappears off into one of these Y rows that we don't usually look at. But of course, here I just applied a controlled Z without choosing which is going to be the control and the target qubit, because it is not required. It is completely symmetric. All you have to do is choose what qubits you're using, what 2 qubits you're using, and the notion of which is control and which is target is completely up to the stories you like to tell yourself about what your algorithm is doing. Now, in a previous exercise, we built an X from a Z and some H's. In exactly the same way, we can build a controlled X from a controlled Z. So for example, now we need to turn on the Z output of qubit 1. We need to turn that on. We can do this with an X here, but that's not something we're allowed. We could do it with a controlled X. If we controlled it here, then it just means, and targeted it over there, then it just means an X would happen on this qubit on the right and do exactly what we want. But we don't have a controlled Z. What we have is, we don't have a controlled X. What we have is a controlled Z and a Hadamard. So what we could do is use the Hadamard to move. We could use the Hadamard on the qubit that we need to use the Hadamard on to move that up here, and now a Z would flip this value. But as I said, we don't have a Z, but we have a controlled Z. Let's control it on this qubit, target it on that qubit. Oh, I fell into this ever so human trap of coming up with this story of what a controlled Z does again. We can also think of it in this way that it just swaps these 2 values, and we want this to be white instead of black. So, and we want this one to be black instead of white. So let's put them in the positions we want them to be. So we can think of it in this circle swapping way. We can think of it in terms of this is the control and this is the target. You can think of it however you like. The controlled Z doesn't care. It just does its job. And now this is on, which is what we need it to be, but we need it to be down here. So let's do, again, the wrong Hadamard and undo the effect and do the right Hadamard, and we have what we need. Okay, so since we're also able to interpret the controlled Z backwards, it also gives us an alternative explanation of what the controlled X is doing. So here we need to turn on the X output of qubit 0. So qubit 0 is this one over here. We need to turn on that X output, and we can do that if we have a Z. So if we had something that has the effect of a Z, then we could do that. But of course, oh, I did allow us a Z, but on the wrong qubit. Man, why am I giving myself the tools I need? So let's do that, since it's obviously, I've given it to myself for a reason. And now this is on, but we have a controlled not, we have a controlled X, but a controlled X, usually we tell the story that it looks at the controls, the measurement outcome for a Z measurement, and based on that does an X to the target qubit. And here we have that the X measurement is certain to output a 1, and we need to do something to the effect. We need to do a Z over here. So that's not what a controlled X does at all, at least according to what the story that we have about it. But oh well, there's not many gates that I've allowed us to do, so let's just do it. No, it works. So we can see here from the effect of the CX gate, the controlled X or the controlled NOT gate, that it also has the effect. We can tell ourselves a story that it looks at the at whether the X output of the control of the target qubit is on or off, and if the X output of the target qubit is certain to output a 1, then it will do a Z to the control qubit. So we can think of the control as being the control and controlling it by whether the Z output is on or off, or we can think of the target as the control. It's just, these are just stories that we tell ourselves to help us understand what's going on. But in the end, a controlled Z does a controlled Z's job, and a controlled X does a controlled X's job. There are multiple different ways that we can try to understand these things, and there's multiple different ways that we can use them, and we can use these to transform them into each other. Okay, so this is, here I have taken you through the notions of X gates, Z gates, H gates, controlled Z, and controlled H gates. These are these form these form the Clifford group of 2 qubits. They are a very important basic set of gates. With them, you can't do general arbitrary things, but you can do some exciting things. Now, we've only got 5 minutes left of this session, and I don't want to run over too much. You can, especially because this is something that you can go through yourself, and indeed it was designed for you to go through it yourself. So you can go through and understand some of these additional things. There are also gates called, well, unimaginatively called non-Clifford gates, which have more interesting effects. For example, this is the RY gate. Let's apply it to qubit 0. It took something which was definitely off and, well, let's run it again so we can see. So this is random, and this is definitely going to output a 0. We do an RY, and now this definitely going to output a 0 has become most likely going to output a 0. And this completely random, whether it's 0 or 1, becomes most likely going to output a 0. So it's done something which has taken this very definite state, which is either definite for a Z measurement or random for an X measurement, and spread the certainty out. We can do it again, and we find that actually now it focuses the certainty for the X measurement and makes the other one random. We can do it again, and it starts spreading it out again. This is most likely going to be 0. This is most likely, sorry, this is most likely going to be, this is most likely going to be 0. This is most likely going to be 1. We do it again, and now certainty is back over here, but it's flipped the value. So yeah, these are things that you can do. And there's also an extension to the visualization, which tries to make this a little bit more easy to understand. So instead of having just on and off circles, an on circle, so one that's fully white, has been replaced by a bar, which is fully white. And the gray one has been replaced by a bar, which is half white and half gray. Now, if you were to, oh, I pressed the wrong button there. And now I have to restart the entire notebook. But yeah, this is, we should be drawing to a close anyway, so that's probably a good sign. So to understand non-Clifford gates, we should really look at other notions. The best way to understand non-Clifford gates in terms of just a single qubit is using the Bloch sphere. So if we did these RY rotations over here using this representation of the Bloch sphere, we see that what it does is, well, this point at the top here represents a state that is definitely going to output a 0 for a Z measurement. This state at the bottom here is definitely going to output a 1 for a Z measurement. And we can see once, and on the equator, it's random whether it's going to be 0 or a 1. This state here represents where you're definitely going to get a 0 for an X measurement. And then you can see how this RY manages to start sharing out the certainty between these different states. So we're not going to get into the later puzzles where we can really get into visualizations of these states and other interesting effects, but this is already an hour on thinking about qubit states, thinking about the outputs you get from qubits, thinking about how they differ from normal bits and ways of manipulating them. And even though these are in some ways the simplest gates, these Clifford gates, they are also the most important gates. And if you wanted to, for example, contribute to our compiler, probably understanding these gates that we've looked at so far are the most important ones to understand. If you want to work on quantum error correction, it is all built out of these gates. So if you want to build quantum algorithms, you will need to learn about more gates, and you can do that by going through the rest of these puzzles. But I think this is a good place to leave it because you already have the basic idea of how to manipulate at least a pair of qubits. So now I think if there's any questions, we can take questions, and otherwise we can have a break before the next session.
The Microsoft link is available.
Hey, James.
Hey.
We all fine here. We replied already to some questions in the chat. We don't have many. We don't have any question actually, which hasn't been replied. So we can all take a break. What do you think it could be a reasonable amount of time?
I think let's go for 10 minutes. Anything lower than 10 minutes is not really a break.
Agreed. Okay, perfect. Then we meet at 10 past 6.
Yeah.
Thank you.
Okay. See you then.
See you then.